Now we're going to talk about net ionic reactions. So if we look at our precipitation reaction, we turn to this idea of potassium iodide, lead nitrate combined to give you potassium nitrate and lead 2 iodide. And so if we think about what's going on, in the reactant solution, all your ions were dissolved. And when you go into the products, the K plus and the NO3 are still dissolved, right? You still have AQ right here, which means they stay dissolved. And it's important when we have ionic compounds that are dissolved, the ions are just free floating from each other. So we can see in the reactants, the K plus cations and the nitrate anions are just floating around by themselves. They are paired with a counterion in that solution, but they're not interacting with each other. They're just kind of floating around by themselves freely. And then in the product, the individual ions are still seeing the exact same thing. They're just floating around in water, none the wiser to anything that has happened to the lead and the iodide atoms that have formed this solid. We call this idea spectator ions. These are ions that don't actually participate in a reaction. They don't actually do anything. They just watch it. That's where the word spectator comes from. They're watching the actual chemistry occur. They're not participating in that chemistry. So if we look at this example, if we want to identify what the spectator ions are, we know that when we write this Ki aqueous, Ki is an ionic compound, and we're saying that it's aqueous. We're saying that it's dissolved in water. What that means is that the ionic compound dissolved in water, we know that it's really K cations and iodide anions, right? We have really those cations and anions that are floating freely. So, for the sake of, legibility, we write, the whole compound formula, but in reality, there's ions floating around. And that's what this AQ means. That AQ means that those ions are free floating in solution. If we have a solid, say in this case the lead 2 iodide, that does not separate. Those ions are locked together in the solution. It is not aqueous, it's solid. And so the solid stays together. So this top reaction is called like my overall reaction. I'll indicate it. That's the overall reaction. It shows all the compounds. This right here would be called the total ionic equation. It's not really much use besides just showing all the ions and as an intermediate to our next step. But it really is just kind of a most comprehensive description of everything that is involved here. But one of the things you'll notice is that we have ions that show up in the exact same way on both sides of the reaction. And we've previously said that we don't want to have that, right? That implies that they haven't changed. We don't want anything showing up on both sides. We should cancel them out. These are spectator ions. The K and the NO3 don't change. They're floating around freely in solution. They're floating around freely in solution. We can cancel them out and generate our net ionic equation. The net ionic equation shows you have a cation, you have an anion, and they combine to give you your solid precipitate. This is a precipitation reaction. The net ionic reaction shows the net change of ions involved in this solution. It doesn't show the potassium or the nitrate because they're not actually changing. Now, the net ionic equation is meant to focus in on what the change is. Overall reactions, like this top line up here, are still very useful. It tells you what you actually did. You actually mixed a solution of potassium iodide and lead 2 nitrate, and then you got the solid lead 2 iodide, and you still have a solution of potassium nitrate. It's important to note that the net ionic just shows where the change is. We primarily use still overall reactions just to describe everything that's going on. You cannot go into the lab and find a solution of just lead 2 cations. That doesn't exist. It has to be with an anion. And the nitrate is important here. The nitrate is what makes it dissolve, right? That's rule 2 of our solubility rules. They're always soluble. So the only way to get that lead 2 dissolved floating around in solution is to have it paired with a counterion, an anion that wants to be dissolved. So that overall has its purpose. That's primarily what we use. And the purpose of these net ionic equations is just to really focus in on what you're actually looking at, what the actual change is. Let's do an example. Write the net ionic equation for the reaction between BaClO3, that is barium chlorate, and Li3PO4, that is lithium phosphate. Both are aqueous. So we can see that we want the net ionic equation. This is a chemical equation, so normally we could start with I want reactants, I want products. But net ionic equation, really, if you want to start with that, the question is going to be, what's the overall reaction? What is the overall reaction equation that you have? You will note the reactants I've chosen are not random. These are the reactants that I did from the last example. And so that gives us the overall reaction. Barium chlorate plus the 3 barium chlorate plus the 2 lithium phosphate gives you barium phosphate solid and 6 lithium chlorates. So there's my total reaction. When I want to go about the process of creating a net ionic equation, we follow what I did previously. You separate ions. Anything that's aqueous, that's a dissolved ionic compound, gets separated. We don't separate out solids. That stays locked in. Then you cancel spectator ions. So let's take a look at what that actually looks like. All right, so when we want a net ionic equation. So a net ionic equation is a form of a chemical equation that more information in the reaction. And so one of the things you'll note is the reaction between the compounds we already saw. So what we just need to do, if we want to get the net ionic, we also want to start with the overall reaction. So I'll go ahead and write that out. 3Ba ClO3, 2 aqueous. We do want to keep the balanced part. 2 Li3PO4 aqueous becomes Ba3PO4 2 solid plus 6 Li ClO3 aqueous. All right, so this is what we wanted. We always want to start with the overall reaction. So I'm saving myself some time. We're just going to start. We're using doubling up on the last example. But if it was something new, you would always start by figuring out the overall reaction and then pushing that forward into the net ionic. So when we want to get the net ionic, what we want to key in on is everywhere that is aqueous. We can see that these are aqueous ionic compounds. So that's fine. That means the aqueous compound, that ionic compound, is dissolved in water. But we know that what that really means is that the ions are separate from each other. So net ionic, when we see this ionic, means we don't want to describe our ionic compounds as full compounds. We want to describe the individual ions. So what I need to do is everywhere I see AQ, not S, but everywhere I see AQ, those are soluble compounds, and those ions want to be written separately. It needs to be in a balanced way. So the 3 goes to the Ba, the 3 goes to chlorate, the 2 is also there, the 2 and the 2. That doesn't dissolve, the 6 and the 6. Okay, so that 3Ba becomes 3Ba2 plus. This is going to be a tight squeeze. That stays AQ. Plus, for the chlorate, ClO3 minus aqueous, that 2 and that 3 apply to it. Each formula unit has 2 chlorates. There are 3 of them. 3 times 2 gives me 6. Plus, for lithium, it's 2 times 3 gives me 6 Li plus. 2 times the phosphorus. There's no chance I'm going to fit these products. So what I'm going to do is I'm just going to drop down to the lower line. These become, so there's my reactants, here's my products. Barium phosphate is a solid. That just stays together. It doesn't dissolve in water, so the ions don't separate out, become aqueous. Whenever we see solid, that saves us space and time for coming up with a net ionic. The lithium chlorate is though, so that'd be 6 Li plus aqueous plus 6 ClO3 minus aqueous. So what we've written right here is usually called like complete ionic or ionic equation. Generally, these aren't super interesting. It's just a more convoluted, more kind of explicit way to write all of this stuff that we have up here. So instead, we tend to move forward into the net ionic, which we care about. And so net, when we want net ionic, what we want to focus on is things that aren't changing. Or net ionic is only focused on things that change. So we want to look at things that don't. If we look at, for example, barium chlorate means in your reactants you had barium ions floating around and chlorate ions floating around. Well, lithium chlorate is soluble, so that's really lithium ions and chlorate ions. These chlorate ions show up on both sides of the reactants in the same format, same number, same exact ions. They're floating around by themselves. They are floating around by themselves. Those are my spectators. So once I get to this, I want to cancel the spectators. So chlorate shows up in the exact same dissolved independent state on both sides. The lithium also shows up. So those are what I want to cancel. I guess I should have noted up here, we separate dissolved ions. So that is step one. And now we cancel the spectators. Basically, spectators is literally, the word is the same word that's used for like a, sporting event. Barium and phosphate change. Chlorine and lithium don't. They're not part of the action. They were floating around by themselves before, floating around by themselves afterwards. There is no change for them. They are simply watching the action. So where there is a change is right here and right here. So 3 Ba2 plus aqueous plus 2 PO43 minus aqueous becomes Ba3 PO42 salt. And this is the net ionic. Net means you only focus on the change. Ionic means it's ions in there. And so the purpose of this is to show explicitly where the change is, right? Exactly what the chemical reaction that's happening is. And you'll note these are all precipitation reactions. The net ionic equation really focuses in on that. This, you've got all these different things going around, barium chlorate, lithium phosphate, make barium phosphate precipitate, and lithium chlorate is then dissolved. The net ionic focuses in on just what the precipitation is. Barium cations, phosphate anions combining to give you barium phosphate precipitate. So that's the goal and the purpose of these net ionic equations. So net ionic equations are a general idea, not just in precipitation reactions, and they allow us to focus in on explicitly what is changing. And so in a precipitation reaction, they're always going to have this characteristic form. Ion plus ion leads to solid, because that's the characteristic reactivity of a precipitation reaction. This is what we would always expect to see. We also do want to make sure it's balanced. We have all our phases. Those things are also there. But as long as we were started from balance, we should be good going. So one of the purposes of the net ionic equation is really to focus in on what the reaction actually is. What change do we have? So precipitation is forming a solid. And we've seen in previous in the lab and in previous cases, that formation of a solid is evidence of a chemical reaction. And so if you mix two solutions and no precipitate forms, then no reaction occurs. So if we look at, for example, something like the equation that we're given, sodium chloride plus potassium nitrate, those react to give you sodium nitrate and potassium chloride. Those are all soluble compounds, so they all keep the AQ. They're all aqueous. So there's no solid products, which we can note. So these tend to, we wouldn't call this a precipitation reaction. So what is it? Well, if we separate out all our ions, everything is soluble, so everything gets separated out into the ions. And then if we go to cancel everything, well, everything's a spectator ion, right? Because if we look, we can see we got sodium, sodium. We have chloride, chloride. K+, nitrate, nitrate. Everything is on both sides, so everything's a spectator ion, and when you cancel it, you are left with nothing. There is no net reaction that occurs, which is confirmed by the fact that your products are both aqueous. You started with a bunch of dissolved ions, you've just ended with a mix of even more dissolved ions, but there's not been any net change. And so the lack of a net ionic equation, the fact that if everything is a spectator, then there's no event. There's no reaction that occurs. So the purpose of these net ionics is really to focus in on what reaction has occurred. And in precipitation, that's formation of a solid, and that's why the net ionic equation really just features cation plus anion leads to a solid.